a comparator, what we do is we usually compare two voltages. Okay, so the next topic is comparators. So before we draw the circuit, as always, just write down few points here. Okay, number one, compare one voltage to another. Okay, that's one application. And this is an op-amp circuit, right? Is an op-amp circuit, okay, without negative feedback. We don't have a negative feedback in this case. Okay, so we don't put any kind of feedback into the system here. Okay, so if there is no negative feedback, the voltage gain would be nothing but the open circuit gain. So that we have already studied that voltage gain is equal to A. Usually we write it down as OL. Okay, open loop voltage gain. Open loop in this case we actually have it as this. One more point, we do have two input. Okay, here in this case it depends on what you are comparing. If you're just taking up one voltage, the other one can be put at 0. Okay, so but still it's a comparison. So we basically have got two input voltages, okay, and one output voltage. So this is OL. Okay, so let's just draw the figure. Okay, fast. It's simple. So we will just have the one in output. That's every time we have seen that. Okay, so that's one on output here. And then two inputs here. And then what is more important is the driving voltage. So when we actually studied about the interior of the op-amp, when we're talking about it as an amplifier, and we talked about two transistors being coupled, okay, and we have that part as an op-amp section. There we said that there is a biasing voltage that we have, and that biasing voltage plays a very important role in this case. Okay, so this is what we're going to look into now. So the output can be taken across a load resistance. So we can just draw a load resistance here. And as I said, the driving voltage would be there. Okay, and this will be a typical value would be nothing but 15 volts. Okay, so this is plus 15 volt, let's say. Okay, and this is the other end, which is minus 15 volt. So these are some typical values that we usually use. Okay, this is your non-inverting terminal, this is your inverting terminal, and as I said, we will have two different voltages. Okay, so we have this, and then let's say this is your V2, okay, and this is the other voltage, which is V1. So by comparator, it means that we can actually compare these two voltages of V2 and V1. Okay, and as a result, we can actually give out that result. So this is a typical circuit, and whatever may be the output voltage, it cannot be more than 15 volt, because that is the driving voltage that we have. Okay, so you have to keep these things in mind, and based on this we can actually write down few more points. Okay, So we will just write down this. Okay, it has a saturation, okay, value as the DC saturation value as the DC supply voltage is 15 volts, right? So it has got a DC saturation value because it will actually depend on the supply voltage, okay, and that's around 15 volts, okay. So that's your 15 volts. So in saturation, it means that this V out uh, cannot be greater than 15. So the saturation value cannot be greater than 15 volt, and that is important to understand here. Okay? Just mark this out here. So the saturation voltage, this is 15 volt, and then that means V out cannot be greater than this 15 volt. Okay, so that's something which we need to consider in this case. And then this comparator can again be used in different kinds of circuits. Okay, and just write down this. Okay, comparator as comparator as. Let's write down some applications here. So we can also use a comparator as a square wave generator. Okay, wave generator. Okay, we can use it as a zero crossing detector, as a zero crossing detector. Okay, and finally we can also use it as a level detector, just going to discuss one by one briefly, okay, all three of them. So let's just have a look at the first one, square wave detector. Okay, square wave detector. Okay. Let's see how it works that way. So what does it mean? It means that you are going to get the output of as a square wave. Okay, so the output will be a square wave with respect to an input. Okay. So we will have a square wave output. Okay, from. So this is what is a square wave detector is all about. Okay, so we will have a circuit which is actually similar to this, so don't need to redraw this. Okay, I'll just take this up. Okay, and then you can actually measure the output. So we can actually measure the output across this. Okay, so let's take the output here. Sorry, so we can just take the output across this. It can be measured. Okay, and then we have got an input as a wave or a sine wave. Okay, so it's not always mandatory that you need to have two inputs. One can be grounded. Okay, and if one is grounded, it means that we are actually doing a comparison of v1 minus v2 where v2 is equal to 0, right? And in this particular case we can say that this is the input here, this is the input, and then the signal might be a sine wave. Okay, so this is a sine wave, and at the output we will be actually having, I would suggest all of you to just have a look at the first part of op-amp that we have studied. This is 13 volt, and let's say on the negative side also this is 13 volt, and an op-amp is typically ran by a biasing voltage of 15 volts. Okay, so you'll get a maximum of 13 volt on the positive end and the maximum of 13 volt at the negative end, and in this way you are going to get a square wave output. Okay, so this is how it works as a square wave detector, right? So this particular part which we have here is saturation, we set. So that's plus 13 volt, and this is minus V set minus 13 volt. Okay, and this particular line that we have is usually called a zero line. So we are going to use the concept of zero line. Okay, zero line. This is the zero line. Okay, so what we have is the variation on both. And and let me just write down a few points here. First thing, maybe we can talk about Vin. Okay, and you can note this Vin is applied to the non-inverting terminal. Okay, so applied to non-inverting terminal. Terminal. Okay, this is the non-inverting terminal, and the gain is open circuit gain now. So since gain, okay, is equal to AOL, okay, the open loop gain. Okay, now what happens usually is that if there is any kind of difference, okay, let me just write it down, virtually any difference with will give the output okay, as saturation value, as saturation value. That's 13 volt in this case. Okay, saturation value. Now why is that? Because this is going to work at 13 volt and minus 13 volt within this range. So whatever may be the difference, the output voltage is not going to cross this maximum 13 volt value. Okay, so you are going to get the saturation value. Okay, then in this way you are going to get a form of square wave that we can see in the image. And what happens is that after you show this diagram, you have to just write down few points. So these are the points that you have to write. Okay, the saturation value point is important. And then secondly, you might also write down this. Okay, when input goes to goes goes to positive, we basically have the output is 13 volt plus 13 volt. Okay, and then when input goes to negative, output is minus 30 volt. So why this is important? Because if there is a difference which is, let's say, around 20 volt or 30 volt between the input and the output, okay, between the input or the two input signals that we have, let's say this V input is around 30 volt or 20 volt, you're not going to get an output greater than 13 volt. Okay, because that is the driving voltage that we have. Okay, so that saturation value is going to be achieved. So one of the application is actually to just convert a sine wave into a square wave. Okay, next we actually have it as a zero crossing detector, right? So that's the second point here. So number 2, we basically have it as zero crossing detector, and I think we can guess it because we had the zero line, and as soon as there is a fluctuation from positive to negative or negative to positive, we can actually understand it using this logic. Okay, so similar to square wave detector. Okay, square wave detector. Okay, we can detect the change from negative to positive or the other way. Okay, negative to positive, that is when the signal is low. Okay, so maybe the signal is sorry, not low, when the signal crosses the zero line, right? So you can know or you can understand about the change of polarity when we are actually having the crossing of the zero line. Okay, and that is why we are talking about zero crossing detector here. Okay, so there we really don't need to do much or understand much. And finally, the third one is as a level detector. Okay, so one of the voltages actually can be taken as reference here. Okay, and then we can actually do the calculations here. So what happens is that in general you can have one voltage as V input. Okay, So you can actually have it as V in this one, and the other one, which is actually V2, this actually can be taken as a reference voltage. Let me write it down, REF. Okay, so if you have a reference voltage and you have a voltage which you want to measure, you can say that how much above or below the reference voltage is the input voltage. Okay, and that is the application of it as a level detector. Okay, so here also, of course, whenever you are doing this basic thing, you should just draw this V output, V out. Okay, so this is a level detector. So how do we use it as a level detector? It is actually used to similar, like we are doing a comparison. So this is actually working as a comparator, no doubt. Okay. So just write down these points. Okay, used to compare uh, signal amplitude. Okay, fixed DC or AC. Okay, we can actually do a fixed DC. No, DC would be better because we don't want a reference signal which is varying. Okay, we can probably use a DC signal. Okay, it is mostly used here this way. So let me just use a battery here. Okay. To a fixed DC. Okay, voltage. Reference voltage. So sometimes it happens that if you have a circuit and you want to have some kind of detector, okay, and you want that above or below a certain voltage, the system should not work, or if it goes above that certain specified voltage, there should be an alarm which should go on. Okay, so these kind of applications might be there when we actually use these comparators. Okay, so used as a signal amplitude to fix DC, which is the reference voltage. Okay, and this circuit is referred to as the level detector. Okay, so that's your level detector that we have. Okay, and in general what happens is, in this case, when there's V in, okay, so this V input voltage, okay, is less than V reference. Okay, this V out will basically go to max level. Okay, max negative level, let's say. Let's take the other one, negative level, and remains here until the input, okay, is above V reference, is above V reference, and vice versa. Let me just fill it up for you. What happens usually is this. Okay? So what happens is, if V in, okay, is less than V reference, so whatever voltage you have here, the input voltage that you want to compare, is less than the V reference, then this V output, okay, will actually go to maximum negative level. Okay, because this is less, so this will actually go towards the negative level and remain here. Okay, until this V input, okay, is above V reference. So once this V input goes above the V reference, it will actually shift to the positive side. So this is also a kind of zero crossing detector. Okay, this is also a kind of zero crossing detector, which is nothing but the level detector. Just a sec. I think I did not put the heading as such. 1, 2. Okay, I should put the heading here. Yes. Zero crossing detector. We have seen this. Oh, it's there. Okay, that's fine. Just make this yeah. Confusing here. Okay. So this is about the comparator. Okay, so this is about the applications of op-amp in different uses. Okay, so you have to just look into this, and the questions might be objective as well as descriptive, as you can see. Okay, so that's it. So this is actually a large topic which we have finally finished. Okay.